Hey everyone. In this next section, we're continuing our study of waves, but we're going to be looking specifically at sound waves. Okay, so the first thing to note is that sound waves, they follow all the same properties. We talk about the amplitude, the frequency, all of those properties of reflection and diffraction that we looked at with regular waves. All of those things still apply to sound waves. Okay, they're just a particular type of wave that we're going to study. So the first thing about sound waves is they are a mechanical wave, and they're what we call a longitudinal mechanical wave. So remember, a mechanical wave requires a medium to travel through. Okay, so they're made up of a series of compressions and rarefactions. What that is, so imagine a speaker producing a sound wave. So we have the speaker over here on our left. Okay, when that speaker pumps, and we'll see a little video of this in a second, but when that speaker moves in and out, so it causes all of the air particles here to compress. Okay, these are what we call our compressions. And when it compresses, it then, as the speaker cone moves back in, the air particles actually pull apart a little bit in this next area. So we have things spread out, and we call that a rarefaction. So this speaker moves in and out over and over and over, or whatever's making the sound, a voice box, something that's vibrating, creating a sound, and causes these compressions to happen, which then send the wave out. That wave, then in the case of humans, okay, travels into our ear and hits our eardrum, and it causes our eardrum to vibrate, and that's what allows us to pick up the sound. So it actually would repeat the similar vibrations that come out of the speaker due to those compressions in the air, and we hear various sounds. Okay, so here's an example. Here's an animated example of it. So we see the plunger here representing the speaker, okay, or whatever's creating the sound that's vibrating. As it moves forward, it compresses the air, and as it moves backwards, okay, it rarefacts the air, or decompresses it, lets it separate out a little bit. And we can see these wave fronts. So the compressed areas are the wave fronts that are traveling down. We can represent this as a traditional a transverse wave, as we've been looking at before down below, where the compressions represent our highest point of amplitude. So that's where we would hear our sounds, and the rarefactions are the lower points. Okay, so that's the minimum and maximum points. And just like a wave, it's a transfer of energy. So if you look at those red dots that are positioned in there, okay, they do move back and forth a little bit, but remember, a wave does not carry particles with it. Okay, the air vibrates in this pattern, but stays, it doesn't, the air particles don't travel from the source of the sound to your ears. It's just the compression and the energy does. If you've watched the show, I believe it was Big Bang Theory, had the speaker that they showed bouncing. Okay, here with the whatever, I can't remember what was on top of it, but here's an example of one with paint. Okay, so if you actually look at a speaker, if you have a large enough speaker, like a bass speaker or something, and you look at it while it's playing the music, you can actually see it vibrate. And those vibrations, as you see here with the one with the paint on top, those vibrations are what's creating those compressions in the air that's allowing the sound waves to travel forward. The different properties of sound when we talk about it in terms of waves. Okay, we have the loudness, which is the amplitude. Okay, so the larger the amplitude, the more energy our sound wave has, and that is how loud we're going to hear the sound. So small amplitude is a very quiet sound, and a big amplitude is a very loud sound. The pitch, so if you're used to playing musical instruments, okay, you have your scale A through G, your 8 notes that go up, and your sharps and your flats and all of that stuff. Well, this is what's talking about the pitch. Okay, so the pitch is what the frequency determines. So a higher frequency, so if the wave fronts are closer together, that is a high pitch, whereas a low frequency would be a bass sound or a low pitch. Okay, and the last one is quality. And what I mean by quality is for example, everyone here has probably heard a guitar and a piano play. And they have very different, distinct sounds. Yet both a guitar and piano can play the exact same note. They can both play, say, a C note, and they can both play that note at the same volume. So they're both a C, they're both in tune, they're at the same volume, yet you can still distinguish the difference between the sound a guitar makes and the sound a piano makes. Okay, and this is what we talk about the waveform or the quality. So each thing that produces a sound um, will produce its own individual distinct type of sound. For example, I can try all I want. I could sing a C note in the same volume as a guitar, but my voice will never sound like a guitar. For humans, the range of hearing, okay, human hearing goes from a sound of 20 hertz to a sound of 20,000 hertz. Okay, so below 20 hertz, the pitch is too low, so we call that infrasonic. And above 20,000 hertz, we call that ultrasonic. Okay, this range decreases as we age. There's a lot of fun tests. You can find apps on your phone or tests online where you can actually go on and try it. Go look up a frequency test or sound test, and you can try to see where your range currently lies. Now, it does depend on the speaker quality that you're listening through as well. If your speakers can produce those low and high sounds. But it is just a fun, neat thing. So check out again a frequency test online. See if you can still hear up at the 20,000 hertz. Again, this is the average for human hearing. It does decrease as we age, and a lot of animals can hear above our hearing range. So that's how a dog whistle, for example, works. A dog whistle plays a sound that would be ultrasonic to humans. So when we blow into it, a human can't hear it, but a dog's hearing can hear at much higher frequencies than us, so they can actually pick up the sound of the whistle. So I mentioned that sound waves before are mechanical waves, which means they need a medium to travel through. Okay, and the medium they travel through determines the speed of sound. So whether they're traveling through, say, air or a solid object or a liquid or anything. So here's some different materials. So air, speed of sound travels at 331 meters per second if the air is at regular or 0 degrees and 101 kilopascals of air pressure. Travels at different speeds through different types of air. So if we have pure helium, the speed of sound is actually faster. And this is why when you see people breathe in helium balloons and their voice gets really, really high pitched, that's because the speed of sound is actually increasing in helium, and that has to do with its density. Okay, in water, we see the speed goes up even more, and in copper and steel, it goes up even higher than that. And it may seem odd at first. Why is the speed of sound increasing in solid objects? Wouldn't it go faster in air? But hopefully this will help understand a little bit. So air molecules. Okay, the molecules in air are spread out a lot more than they are in a liquid, and a liquid's spread out a lot more than they are in a solid. So remember, air requires the vibrations to travel from one molecule to another molecule in order to transfer the sound. So the farther the molecules are apart from each other, the longer it's going to take those vibrations to transfer. So in a solid where everything's packed really close, the sound can actually propagate extremely fast. This is why if you ever watched an old movie with a train, when people put their ear up to a train track and try to listen, okay, is the train coming? The reason they put their ear to the track is because you can hear the vibrations of the train through the solid metal track faster than you could hear it coming through the air. So you can know if it's coming from a quite farther distance away. This idea also has to do with why there's no sound in space. So if you've watched Star Wars and you have the ships flying around and things are exploding and there's lasers shooting and you hear the noises, you actually wouldn't hear any of that if you were up in space. A space battle from an outside perspective would actually be quite silent because there's no medium for the sound to travel through. Okay, in air, our speed of sound equation is 331 plus 0.59 T, where T is the temperature. Okay, so in Celsius, T is the temperature in Celsius. So as we increase the temperature, the air molecules can actually move faster, allowing sound to travel faster. So at a higher temperature, we have a higher speed of sound. At low temperatures, we would have a lower speed of sound. If we have things moving faster than the speed of sound, okay, at a particular temperature, we call that supersonic. Okay, so for example, a jet breaking the sound barrier creates a sonic boom. So that cone that you see behind it is all of the air compressing from the sound waves. So the sound waves are compressing all the air very rapidly directly behind the jet as it breaks the sound barrier. Okay, the Mach number, how we study these things moving faster than sound, is we use what's called the Mach number. And all it is a ratio of the object's speed, their object speed to the speed of sound. So the velocity of the object is on top and the velocity of sound is on bottom. So if we have a Mach number of 1, if something's going Mach 1, that means it's going as fast as the speed of sound. If it's going Mach 2, then it's going 2 times the speed of sound. Okay, a little bit about how these sonic booms are created. So sound, we can think of sound as being created from a point source. So for instance, when I speak, regardless of the direction I face, my sound can be heard in a 360 bubble around my mouth or where my voice box is creating the sound by its vibrations. Okay, so we can represent sound as coming from a point source like in this diagram. Now what happens when we start to move that point source? And we'll talk more about this when we study the Doppler effect later on. But when we start to move that point source, it starts to compress the sound waves. So as the source moves, the sound waves kind of echo out behind it. If we move fast enough, if we move at the speed of sound, for example, then all of those compressions of sound, since we keep moving faster than the sound we're producing, okay, those compressions would all start to stack up like you see in the picture here, and we get this area of really highly dense compressed air happening at the front and then not so much in behind. So this is when you start to break the sound barrier. This compression is called the sonic boom. So as soon as you start moving faster than that, you explode out, you hear that big bang, and that's that large compression of air. So at this point, if something's actually traveling faster than the speed of sound, you wouldn't actually hear any of this because every time your sound is created, you're moving faster than it can propagate forward. Okay, so the sound is always remaining behind your object, which is kind of interesting. And what we get from this is that shock wave that you saw in the image before of the airplane. So we get that cone happening behind it of all that compressed air releasing very quickly, blasting out behind. Let's take a look at an example with some calculations here. So we have a plane flying at a speed of 855 meters per second if the air temperature is 12 degrees Celsius. So let's calculate what is the speed of sound as well as what is the Mach number for the airplane. Okay, so our speed of sound equation for part A, we had 331 plus 0.59 times the temperature. Okay, so we put in our temperature in degrees Celsius, so 331 plus 0.59 times 12, and we get a speed of sound of 338. So that's at 12 degrees, sound travels 338, and that is in meters per second. Okay, and that's part A. Part B, what is the Mach number for this plane? So Mach number is our velocity of our object divided by the velocity of sound. So we have our object is traveling from the question at 855 meters per second, and our sound is traveling at 338 meters per second. So we get a Mach number of about 2.53. Okay, and due to both of these above, so both speeds are in meters per second, okay, our units do cancel. They divide out, so Mach number is a unitless number, so it just says 2.53, which means that this object is moving 2.53 times faster than the speed of sound. Okay, and that's everything for our introduction to sound and sound waves.